Hello everyone, and welcome back to physics class. Today, we are going to be talking about forces. Specifically, we are going to look at the gravitational force. Now, before we start getting into the specific kinds of forces, let's talk about forces in general. A force is a vector quantity that acts on an object and causes it to either deform or to move, or perhaps even both. Let's take an example. Let's say that we have a car that is driving along some pavement. The car is moving forward. The car is moving forward because it's using gas, and the gas is powering the engine, which is causing the wheels to turn. Now, the wheels turning on the actual pavement causes the car to move forward. It actually is a form of friction, which is a type of force. In terms of the car, though, we're going to call this the applied force. So we always denote it as FA. So this is the applied force. Now, everything is subject to gravity. That means that there's a downwards force acting on the car that is our gravitational force. That's what we're going to look at today. The road prevents the car from moving past the road, moving down. So there is a force that's pushing the car up to keep it from falling through the ground, and that is the normal force. Finally, there is the force of friction. Now, I mentioned that the force applied in this case relies on friction, but we're also going to be considering that friction is a force that opposes the motion. In this case, since the car is moving to the left, our friction force is going to move to the right. Now, there are other types of forces like centripetal force and the force of tension, but these are the ones that we're going to focus on in this class. Now, when we talk about the gravitational force is a mutual attraction between two bodies or two objects on account of their mass. So their mass is very important when we calculate gravitational force. When we are calculating the gravitational force between two bodies, we use this formula here. We have force of gravity is equal to our g times mass 1 times mass 2 divided by r squared. The g is our gravitational constant. It is 6.67 times 10 to the negative 11 newtons meter squared over kilogram squared. M1 and M2, they're just the different masses. They're both measured in kilograms, and our r is the distance between the two of them, which is measured in meters. You'll have to be very careful about your units here. You can't use kilometers here. You have to convert that to meters first. So this is the basic formula that we use. Let's take a look at an example. So here we have an example. We have a bowling ball here that has a mass of 7.99 kilograms, and we have a bowling ball pin that is a mass of 1.6 kilograms. The distance between the two of them is 18 meters. So if we wanted to calculate the gravitational force between these two, we would do the following. 6.67 times 10 to the negative 11 times 7.99 times 1.6 divided by 18 squared. Multiplying the top all together, we get a total of 8.53 times 10 to the negative 10, and then 18 squared gives us 324. When we divide that, we will end up with the gravitational force of 2.63 times 10 to the negative 12 newtons. So this is a very, very small number. You can see that when we have small masses and small distances, the gravitational force is extremely low. Obviously, we see this more prominently with larger objects like planets. So when it comes to calculating the gravitational force of objects in relation to Earth, we actually use a simplified formula. Let's take a look at that right now. Now, this is the formula that we tend to use most often when we are looking at forces acting on bodies, because oftentimes the forces that we're looking at are acting on bodies that are on the surface of the Earth. The M stands for the mass, and of course we measure that in kilograms. Now, the G, we've already really seen this. This is our gravitational acceleration. So negative 9.81 meters per second squared. And that's really it for the gravitational force. Now, please note that whenever somebody is asking for you to calculate the weight of something, you use the same formula. So weight is also using this same formula right here. We just don't tend to write this, mostly because we use actually W to represent another thing in physics. But do know that this is the same formula that we use for weight. So let's take a look at an example. We want to know what is the weight of a person that has a mass of 75 kilograms. So remember, gravitational force is the same thing as weight. So we're going to calculate our gravitational force. It is mass times gravitational acceleration, so 75 kilograms. And then we multiply it by the negative 9.81 meters per second squared. Now, when we multiply these together, we're going to end up with negative 735.8 kilograms times meters per second squared, right? This is what happens when you have your units here. Notice how this force is negative, and that's because the force is basically pulling us down towards the ground, so it's a downwards force. But also notice that this unit actually turns into a Newton. This is what a Newton means. A Newton is 1 kilogram times 1 meter divided by time squared. So for this case, you don't have to write the kilogram times meter over a second squared. You can just write it as a Newton. Now, I want to just kind of review the concept of mass versus weight. Mass and weight are related, but they are very different. For instance, if we have an object that has a mass, and we take that object from Earth and we put it on the moon, the mass of that object still is the same mass. Mass does not change regardless of where you are in the universe. Weight, however, is dependent on gravity. So if you take an object on Earth and you put it on the moon, it will weigh less because the gravitational acceleration is less on the moon than it is on Earth. Mass is measured in kilograms. Weight is measured in newtons. So those are the two really big differences between mass and weight. Weight depends on gravity. Mass does not depend on gravity. Now, to kind of bring this point home, let's take a look and let's calculate the weight of a dog on the Earth and on the moon. So let's say that our dog has a mass of 5 kilograms. So let's calculate for Earth first. So mass times gravity, so 5 times our negative 9.81 will give us a total weight of negative 49.1 newtons on Earth. And let's say that we wanted to calculate the weight on the moon. So gravitational force on the moon, we take our mass times negative 1.62, which is the moon's gravitational acceleration, and we will get negative 8.1 newtons. That's a pretty big difference. This demonstrates that the mass stays the same regardless of the location. It is just the weight that changes. Just to review, gravitational acceleration takes into account the mass of two objects. The gravitational force acting on an object will cause it to have a weight. And the formula that we use to calculate the gravitational force of an object is Fg is equal to m times g. Thank you for listening, and I will see you guys next time. Bye!